Hi, my name is Marco, and this project focuses on predicting the net hourly electrical energy output of a combined cycle power plant using Google's AutoML. Our goal for this project is to build an accurate regression model that forecasts power output based on environmental variables such as temperature, pressure, humidity, and exhaust vacuum. So when using Google AutoML, you don't manually select algorithms. The platform automatically tests, tunes, and blends multiple regression models, including linear models, boosted trees, and neural networks to find a best ensemble. I ran two experiments, the first using all four input features, and the second using a reduced feature set to evaluate the impact of the feature selection. So to run these experiments, we're going to follow the following process. We're going to upload the provided CSV file into AutoML. It will then split the data automatically into 80% train, 10% validation, and 10% test. And we'll rely on AutoML to select the appropriate models to run this experiment. We're going to run the experiment for all features, experiment A. For the second experiment B, we'll run it for fewer features. And then we'll note at the end of each run the root mean square error, the mean absolute error, and R squared. And then compare which model generalizes better, primarily using the root mean square error. And then based on that, we pick the best model. I basically used ChatGPT to inspect the CSV data file. The dataset contained 9,568 rows and 5 columns, 4 environmental features, and 1 target, the power output megawatts. All data were numeric and complete, so no cleaning was required. After confirming data integrity, I uploaded the CSV file into the Vertex AI AutoML in my project, which I called my first project, and selected regression as a prediction objective. Once we kick off the training process by clicking the Train New model from the previous screen, we're placed into this workflow. In this case, the first screen is called the training method, in which case we pick the regression as the objective task, and then the model training method is the AutoML, and that's selected by selecting the radio button down below. After clicking the Continue button from the previous screen, you're brought into the next step in this model training process, which is the model details. You'll select the top radio button, Train New Model, and then under Target Selection, you define a target, which is the power output. And in the bottom third of the screen, you select Random for data split. And this basically allows the AutoML to split the data, 80% training, 10% validation, 10% test. And that's illustrated at the bottom of the screen. So moving on, we go into the training options screen, bypassing the join feature store screen, which is optional. I didn't feel like it was necessary for this experiment. In this screen, you'll notice that this is where we select the input features. The target is already selected for us based on our last screen. And this is where we also select the optimization objective. I selected RMSE as the optimization objective because it penalizes large errors more strongly, which is important for energy forecasting where big deviations can be costly. At this point, we set the computing and pricing budget to 2 hours, maximum node hours. There's really no reason to go any more than that. So as I've indicated in the last slide, it took a little over 3 hours to train this particular model. When it's done, you'll see the ready indicator. Clicking the Evaluate tab, you can see the statistical results of our run. In particular, we're going to be looking at the root mean square error as a measure of the performance of the model relative to the next run. A lower value indicates a higher quality model, where 0 means the model made no errors. On the bottom part of this slide, you're going to see bar graphs. Each of these represents a contribution of each of the features, and you can see the ambient temperature and the volume are the biggest contributors to the model. So for the next experiment, I wanted to see how the performance of the model changed if I only use the most influential features. That is temperature and vacuum. To compare, I ran a second experiment using only ambient temperature and volume as features. This simulates a simpler sensor-limited configuration. What's next is to reopen the same database, train a new model, exclude the ambient pressure and relative humidity, and train with the dominant contributors, ambient temperature and volume. Keep the same target, train at the same settings, compare the root mean square error, and choose the lower one as our final one. So we basically run through the same process again to train the model. We select the Train New Model button. We set the same target and select the same random splits. For this run, we exclude the ambient pressure and the relative humidity and select as our two features the ambient temperature and the volume for this second run. On the bottom of the screen, you'll see that we leave the default selection for the root mean square error as the optimization objective. For the compute and pricing, again, I select only 2 maximum node hours. There's really no reason to go any higher than that, so I went with the same one. Here we see that the second run finished. Here we have the statistical result of the second run. In particular, we're still looking at the root mean square error. For this run, it came out to be 12.662, which is higher than the first run. Down below, again, we have the contributing features. Although it shows all 4 bar graphs, we only ran this for the ambient temperature and volume. So here we have the results for the 2 model runs. For Model A, where we use all 4 features, we came out with the root mean square error of 3.17, which eventually converges to an average prediction error of 1% of total output. And that was calculated by taking, again, the 3.17 for the root mean square error, dividing it by the 450 megawatt average output. Comes out to be 0.007. Multiply that by 100. Comes out to be 0.7, which rounds up to 1%. Model B, as you can see, was a little higher with the root mean square error of 12.662. So based on these results, the final model chosen is Model A using all 4 features. That turned out to be a better fit, a better predictor for our experiment. So in closing, this slide basically shows the overall outline of the process that I followed. I decided to use the Google AutoML to predict the power output from a combined cycle power plant. And basically, we follow the workflow shown, which is data validation, feature selection for each run, train a model based on those feature selection, and then perform the evaluation based on the matrices that you see here, the root mean square error, the mean absolute error, and R squared, and we use those to assess the model accuracy. Ran the 2 experiments. Model A used all 4 features. Model B used a reduced feature set. And we selected Model A based on the performance based on a root mean square error of 3.14 megawatts. It shows a strong predictive performance. And so with this exercise, we basically demonstrated that AutoML can produce accurate, operationally useful forecasts for energy management. And finally, this project demonstrates that AutoML can efficiently deliver high accuracy energy forecasting models with minimal manual tuning. So that's my contribution, or at least my submission for this exercise. I hope this makes sense, and I look forward to your critique. Thanks a lot.